so in this particular problem, we have two objects of masses m1, which is 100 kilogram, m2, which is 400 kilograms, that are placed at a distance of d, 10 meters apart. Part A asks us to find the magnitude of the gravitational force, or the force of attraction between them. B wants to know what happens if one of the masses is double, and in C it says what happens to the force between the objects if the distance between them is double. Alright, so let's go ahead and knock out part A. Part A is pretty straightforward, just a calculator problem. In order to knock out part A, it's important for you to apply the gravitational force attraction, which is G, universal constant here, times m1 times m2 divided by d squared. G is Newton's gravitational constant, which is 6.67 times 10 to the negative 11. I'm going to skip all this unit here. And then times mass 1, in this case is 100 kilogram, m2 is 400 kilograms, and then the distance given is 10 meters, but we need to use parentheses because we need to square that distance. Okay, so it's important for you to use parentheses in the denominator here. If you simplify all this, kilogram square on the bottom here in the Newton's gravitational constant will cancel out with this kilogram, but it'll also cancel out with this kilogram. Kilogram square suggests that there are 2 kilograms, and then that in the bottom will cancel with the 2 kilograms on the top. So the only unit left in the numerator is Newton times meter square. But at this point, if you notice here, meter square is also going to cancel out with the meter square. But I'll go ahead and distribute the square first for you to see that. Okay. So if you punch in 6.67 times 10 to the negative 11 times 100 times 400 on your calculator, you should get a value of 2.668 times 10 to the negative 6 newtons times meter square. So once I cancel all the kilograms in the bottom and the top, the only units I have left in the numerator is Newton times m square, which is meter square. However, when you distribute the square in the denominator, the square exponent is going to go to 10. 10 squared is going to be 100. Then m is also going to get square, so m squared. But as I said earlier, m squared and m squared is going to cancel out here, so meter squared is going to cancel out. Meter squared is going to cancel out. The only unit left here is newtons, which is capital N. So if we take 2.668 times 10 to the negative 6 divided by 100, we should get a value of 2.668 times 10 to the negative 8 newtons. That is our answer for part A. And then part B asks us to determine what happens to the force if one of the mass is double. So not both of them, just one of them. So what I have done here is I've set up my before and after chart. So the before is always going to be your f of g function, the force of attraction or gravitational force of attraction function, which is capital G m1 m2 divided by d squared, and only change what it wants you to change. So on the right side here, you notice here I put f of g new. So this is my after scenario. So it's just asking to make a comparison. The only thing different is that I put a 2 in front of m1. It said if the mass of one object is double. It didn't specify which one, and it actually doesn't really matter because you're multiplying in the numerator. So here I've just chosen to put the 2 in front of m1. If you want, you can put the 2 in front of m2, and it does not change the outcome. So part B only asks us what happens to the outcome if one of the mass is double. Nothing else changes. So hence the 2 in black there. I'm just going to move that 2 out in the front. Okay, so really here what I'm doing is I'm rearranging the function just so I can pull information out. Multiplying by 2, because you're multiplying, you can put that 2 in the front. And so by doing this, there's a reason why I do this. Therefore, I can regroup G m1 m2 over d squared. So on the left side that I'm highlighting here, G m1 m2 over d squared is f of g. So I can substitute. So G m1 m2 over d squared can be substituted for f of g because it's a true statement. Right, on the left side, the before function says the definition f of g is g m1 m2 over d squared. So anytime I see g m1 m2 over d squared, I can pull that out and I can substitute it out for just f of g. So therefore, my new answer is going to be this. The new force, if you were to increase one of the mass or double one of the mass, would make the force also double. Okay, so it's a linear relationship. If the mass doubles, therefore the force also doubles. So in this case, only one of the mass doubles, and that's our outcome. Let's do part C. Okay. Part C asks a similar concept here. It says, what happens to the force between the two objects if the distance though is double? So here I'm just going to do it in blue. Here, notice I start with my original statement again. F of g is equal to g m1 m2 over d squared. So the before side is super easy to do, right? Just write the function out. On the right side, in the after box, I'm going to write f of g nu for part C. I kept the numerator the same because this particular part C says change the distance between them. It didn't say change the mass. So G stays the same, M1 stays the same, M2 stays the same. But you notice here on the bottom, good habits going to pay off here. It says double the distance. So it is vital that you put this new condition inside a parentheses. Mistakes are often made without parentheses. So make sure when you substitute, use parentheses. So you notice here in the parentheses I put 2D. Putting it inside of parentheses will trigger the fact that you need to distribute this exponent 2 to the 2 coefficient inside the parentheses and also to the variable d. So by doing so, the numerator has not changed, so it's still gm1, m2. But you notice here on the bottom, it is 4, because 2 squared is 4, and then d squared is d squared. And then dividing by 4 is the same thing as multiplying by 1/4. Okay, so I hope here it's not confusing for you. This 4 is in the denominator. I kept it in the denominator. And then I can visualize a 1 in front of gm1, m2. Or you just know that dividing by 4 is the same thing as multiplying by 1/4. So by doing so, I can pull out the gm1, m2 over d squared. And the trick I use in part B, where I highlight gm1, m2 over d squared, and that is equal to f of g, because this is on the before side. Okay, so therefore, instead of writing gm1, m2 over d squared, I can substitute it out for just f of g. You know, this is the original statement on the left side that I'm circling, right? We said f of g earlier is gm1, m2 over d squared. So using the same strategy, I can replace that with f of g. But once again, 1 times f of g is just f of g, and then the 4 on the bottom gets carried over. So here, you would just say that the new force is 1/4 of the original force, because this f of g, which is the before scenario, and if you're going to double the distance, the force actually decreases by 4 due to the inverse square law, right? Anytime you divide by something square, that refers to the inverse square law for this particular unit. All right, I hope that helps. Stay nerdy, don't be white.